I'm just going to start this off a little bit, just talking about the spatial multimodal analyses that or rather how to put these together in the first place. And then after me is going to be Jingxiang, who's going to show us how to actually perform those steps in Giotto. So first, I'm just going to go behind and talk about like the background of it, and also a little bit about the math that's needed in order to get all of your data into the same coordinate space. So the overview is that spatial multimodal datasets are created when there is more than when there's more than one modality that's available for a single piece of tissue, or maybe even like adjacent sections. So yeah, one way you can make these data sets are just by performing more than one spatial assay on closely adjacent tissue sections, or ideally even the same piece of tissue, the same section. However, for these data sets, in addition to the usual expression space integration, you also have to do some spatial integration. You have to spatially align them together so that they map over each other. And that leads me to spatial manipulation. So performing the spatial analyses across any two sections of tissue from the same block, you need to align them into the common coordinate space. Very small differences that happen during the sectioning process. It could be anything from like the cutting motion, how the tissues were sliced off, how long an FFPE section was floated. All of these can result in like even neighboring sections being a little bit distorted when you compare them side by side. And these differences make it difficult to assemble multi-slice and or cross-platform. So like cross technology like Visium to Xenium, multimodal data sets into a cohesive 3D volume. The solution for this right now is to perform registration across either the dataset images or the expression information. So you could either do like image registration where you compare images and then try to figure out how to spatially align them together, or you could do it based on expression information where you look for similarities in how spatially expressed certain genes are and then try to map them together based on those correlations. So one example of that is going to be like PACE2, for example. But moving on, based on the registration results, both the raster images and the vector feature and polygon information can then be aligned into a continuous whole. And ideally, this registration will be more of like a free deformation based on sets of control points or some kind of deformation matrix. But this is a little bit complicated and hard to do. So at the moment, affine transformations already provide a pretty good approximation. In either case, any of these transforms need to work the same way across both the raster and also the vector information. Oh, and I probably skipped over this, but raster is just anything like images, anything that is like binned pixel information, whereas vector data is anything like polygons or points, anything that is explained purely through like numerical values, points in space. And spatial transforms. So these are the ones that we actually support in Giotto. We have these simple transforms and also more complex affine transformations, which we can use to combine and encode more than one simple transform, but I'll get to that in a second. These are the simple transformations. So they are spat shift for XY translations, spin for rotations. This is in degrees, not radians. And we also have rescale for scaling, flip for vertical or horizontal flip across arbitrary lines. This flips across like the zero, the origin by default. T for transpose, very similar to like matrix transpositions. You just kind of like flip it across the diagonal. You have shear for shearing transforms and affine for affine matrix transforms. These I also have some images for in a second. We also have spatial utilities, and these are helpful functions for use alongside these spatial transforms. So there's extent ext, which is actually something that we poured over from Terra. And this is used for finding the spatial bounding box of where your data object is. So if you have some points scattered like from here to here, what's the maximum x min or x min, x max, y max, y min? That is basically your spatial extent. I probably should have had a better like image for that, but yeah. Crop is for cutting out a spatial region of the data. It's usually based on like first the item you want to crop and then the extent of it that you want to crop out, the area that you want to crop out, and then plot for Terra and base plots of the data. So I've already made a couple of like simple plots of the sub objects that you've seen before. It's essentially that kind of thing. And then these are the spatial classes that Giotto actually has that will respond to all or most of these generics that I showed above. So spatial sub-objects are going to be spat box object for XY centroids, spatial network objects, spatial networks between the centroids, Giotto points for XY feature point detections, polygons for spatial polygons. Giotto image is mostly deprecated. We're slowly removing references to this one. And then Giotto large image and Giotto affine image are the currently most used image objects that we have in Giotto, and these are Terra-based images. And then we also have an affine 2D, which is an affine matrix container. It's kind of a utility class that I'll also explain a little bit about in a second. So these are the spatial sub-objects that we have, and this is utility class, and then the overall analysis, the Giotto analysis object itself, also responds to a couple of these spatial generics. So now I am going to move over to my console again, just to show some things. So I'm going to library Giotto, load in our mini VisGen object, set the active spatial units to aggregate in order to, because we have more of the information present in there in that particular spatial unit. And then I'm just going to grab the Giotto polygon out of it. So that just looks like this. And also I'm going to grab the Giotto image, and that looks like this. So these are just some simple examples of the simple transforms that we have. I'm just going to show them with the Giotto polygon mainly. So I'm first going to set up a, not that one. I'm first just going to set up a color scheme. It's just hex codes for a rainbow, and then I'm going to set beforehand the line widths that I want to use for all these plots. And you can ignore like the par part. This is basically just to set up a grid plotting that you can see in, if you're on the RMD right now, or if you're on the book down right now, you can see that it's laid on a grid. That's just for that. I'm not going to run those right now. I'm just going to go straight over to the first line over here that says gpoly plot main no transform. So this is just going to plot my Giotto polygons with rainbow coloring. I did rainbow just because when you do that, it is going to apply it as the coloring scheme across like all of the polygons in order. And that way you can see across each of these spatial transforms, or you can more easily see across these different spatial transforms I'm going to do if I'm making any changes to how the polygons are ordered or how they're oriented in space. It's just a visual aid. Spat shift, so I'm going to shift it to the right by 1000. You can see that these values just switched a little bit back and forward. And so I'm going to do a spin by 45 degrees. And gpoly rescale. So increase the size in the x axis by 10 times and y by 6 times. And then this is just a flip. Oh, and also I should mention for anybody who's not very familiar with these are pipes. So this is just me taking the Giotto polygon without making any permanent changes to it. I'm taking the Giotto polygon, applying a particular function to it, and then, which is the flip, and then it goes straight into plot, which is over here. And I'm adding in these particular params. Main just tells it, this is the label I want. So that's what shows up here. Color is rain. That's the coloring scheme I set up earlier over here. Color is fill with base plot. And then line width is LWD. So these are just base plot parameters. And the nice thing about pipes, I guess, is just that you can do it in the order that things are showing up, as opposed to have it be like a kind of a nested structure. Because if I were to write it in the other way, it would be just like plot, and then after that flip, and then after that it would be gpoly. So I could do that as well, and it's just this. That's essentially the same operation. Okay, so back to this. Next is just transpose to flip it across the diagonal. So if I were to not do that and get rid of this just to make it clearer, this is the original, and then this is with the transpose. You can see how over here, this magenta gets flipped up to here. So it is across the diagonal, and same with the actual values over here. And then shearing is basically, oh, I included too much in there. I should have just been this. Shearing is just taking your current your current y value, and then applying like a multiplicative factor over it. That's how you can think of shearing. It's like toppling over into a rhombus shape. Of course, it also works in the negative direction if you wanted to. And same for y. So one thing to note about some of these, though, is just that some of these do require knowing exactly where your centroid is when you're doing these transforms, or knowing exactly where your center of rotation is, or like, where to expand from when you're doing some of these. So that is mainly relevant for spins. By default, it does spin from the center of whichever extent of the object you have. So you can plot G poly, and then you can say x0 is equal to 0, y0 is equal to 0. And in fact, I think you would, well, not plot, sorry, spin that and then plot it. In general, I think most of the things, if it's related to how to set up a data set for the first time, how to set up a data set that you're seeing from one of the spatial platforms that they've exported, you're usually going to want to set these transforms from x0. So that's just something to watch out for. Oh, spin, yeah. The angle itself I need to set. So 45. Just do note that depending on how you set your x0 and y0, the actual end values for your x and y can be very different. So like this is not the default. This rotations around the center, which is all the way up here right now, are not the default. It's usually around the center of where your object is. So just plot G poly, and then plot the spin, and you see that did not move it very much at all, because this time it's around just the center of this area. So that's also something to watch out for with rescale, because it's usually going to expand away from the center of your item over here instead of from the 0, 0 value. And I guess it's also something you would think about a little bit for flip, but by default, flip actually does go around from 0, 0. So just keep that in mind, and maybe it's something we should update the defaults for in the future as well. But moving on, these are probably better to go back onto the book down for. We just went through this section over here. So affine transforms. The above transforms are all simple to understand in how they actually mechanically work. You can imagine them, if you imagine performing them in sequence on your data set, though, if it's a very large data set with a lot of polygons and points, that's going to be extremely computationally expensive. So luckily, the above operations are also affine transformations. You can think of that as anything to do with, your normal XY coordinate plane, any transform that basically never causes any of the grid of that transform, of that coordinate plane, to curve in any way. Anything that does not require your spacing between values on that coordinate plane to change. So it can't be that 1 to 2 looks like this width, but all the way at like 100 to 101, it looks like this. So there's no warping that's ever allowed with affine transforms, but anything that is not warping, anything that's basically like affine essentially, is perfectly allowed. So it's any of these particular transforms that you can see here. And all of these can be condensed then into a single step. So like I mentioned, there are XY values that undergo a linear transform. These transforms in 2D at least can all be represented as a 2x2 matrix or 2x3 if the XY translation values are included. You can also have these in 3D, but we don't currently support those. So the overall anatomy, I guess, of like a affine transform matrix is this over here. You have like either just this 2x3 3 area, or you can have the entire 3 by 3, except these values down here are not used so much. The linear transform section of it this is the part that kind of like tells how your coordinate plane should behave. Should it entirely shear over? Should it be, you can do a flip over here. You can do like a transpose across, scaling, spinning. All of that is defined inside of this small 2 by 2 over here. And then this 2 by 1 that you have is just for the end xy plus minus values over here, the translate portion. For each of these operations, you can see that I have ripped this particular graphic from Wikipedia. And these are basically how you would define each of these numerically if you were to perform a single, like each of these in a single step. So no change. This is basically your identity matrix. Translate, where you only manipulate your x and y like I showed here. And then you can also like scale. So that's when you change these values instead of like scaling it to 1 to 1. And now you can scale these individual values. So these are all very nice and clean. Yeah, rotation is interesting. It's when you start adding them together that the matrix kind of looks it starts looking very interesting, and it's harder to figure out exactly what's going on when it's applied across a single step. So to perform the linear transform, the xy coordinates just need to be matrix multiplied by the 2 by 2 affine matrix. So at the very end, once you've compiled together your affine from all of these basically building block simple transforms, you can apply that transform in this manner. So where you take the linear transforms, do a matrix dot product with your x and y coordinate values, and then add them to your xy translate values. And that's your final transform value. So it's a single step. The previous part is just accumulation of all of the values into this 2 by 2. And that's done by taking each of your individual transforms, which are defined numerically here. You basically dot product these together in the order that you want to add them. Once you have that combined together, you just apply that end matrix to your xy coordinates, and then that's it. Yeah, so due to the nature of matrix multiplication, you can simply multiply the affine matrices with each other, and then the xy coordinates are multiplied by the resulting matrix. And all the linear transforms are then done in that one single step. So now I'm going to talk a little bit about the affine 2D class I mentioned earlier. Giotto has that as a utility class. It's an S4 class that you can create from any affine matrix. And it responds to the affine transform functions to simplify this accumulation process of a simple transform. So it's like a dummy object, essentially. It's a stand-in for whatever actual data object you have, so that it can accumulate all of those different operations while assuming that it has kind of like the same spatial extent. Because again, the center of rotation, or like center of expansion that you perform some of these operations on actually does matter. So once you have the affine 2D finished up, you can then apply that to the spatial object in a single step using affine in the same way that you would use one of the normal affine matrices. So I'm just going to flip back over to the console now, or RStudio. So I am just going to create an affine 2D. By default, it does make an extent anchor of like negative 180, 180, negative 90, 90. We are probably going to have to come up with a better way of setting this anchor, but this is basically like the defaults that Terra gives you. So if you were to just run extent by itself, that's the usual default extent. It just tosses you. It is recommended that you update the anchor with whatever object you're going to be using the entire transform with. So here I'm going to use it on the gpoly, but if you were to use it with a Giotto object itself, definitely recommend putting that here instead. So I'm going to update the anchor, and this process should also be simplified in the future. Maybe I'll probably like link this instead of like having to access the anchor slot like this. It's probably better to make it respond to the ext generic like that, so that we can essentially do this in the future. Yeah, I'll do that probably very soon. Anyways, back to this. I've just updated I need to actually initialize to make sure it's fully updated. After I've just done that, this is what that looks like. So I have an anchor, which is like the anchoring a spatial extent. It's now mapped to my Giotto polygons information. And it starts out also showing you like a couple of values over here. These are basically just decomposed simple transforms. So you can perform these transforms in this particular order in order to do the exact same thing as your affine. The exact way that those are calculated is, I guess it's not very relevant. It's really just like matrix decomposition. It's not going to be exactly the same things you fed in order to make that affine. It's just a decomposition of the matrix itself. So there's a lot of possible solutions for or ways to get to your endpoint, basically, is what I'm trying to say. And this is just one of them. Probably the most simple one. Affine at anchor is the only way you can access the anchor information. But you can also access the other items, the calculated values for each of those things just by using $ indexing. The actual affine slot over here points to like the contained affine matrix. So as you're adding new transforms, as you're accumulating new items, new transform values in here, it's going to update this particular matrix that you see here. And then this is essentially what gets applied whenever you later run affine on a particular, when you later apply affine on a particular Giotto polygon or any other Giotto subobject, and then you apply like aff, it's going to pull this particular matrix and then run it. Okay, let's see. So I just ran that. And now affine spat shift. So I'm just going to accumulate some of these simple transforms in this affine object. And now you see that it's got some values that are appended to it. I did a spat shift. I did a movement to the right by 1,000 units. I did a spin of 45 degrees across 0, 0, a rescale from 0, 0 by 10 times across X and Y. You have both F and X. First rescale, you do have like both FX and FY, as I showed earlier, for scale factors that you can add. But if you only apply one, then it gets applied to both your X and Y. So that's why there's only one value here. And then flip is going to be a flip across the vertical axis, and then transpose and then the shear. So that all of these have now just been collapsed into this one object of this one affine 2D. And I can take a peek at the affine again and see that these numerical values are updated. So this, again, is what's going to be applied to your XY coordinate points through matrix multiplication. So you can also plot these. Since we have a anchor spatial extent applied, you can actually plot them and then it'll show you like the projected affine transform you're making. So this is your start at the blue, and then this is the endpoint all the way over here that you are applying with this particular transform matrix. Yep. So now I'm just going to apply that particular affine transform, and you can see that it is properly applied to the Giotto polygons. And I think that's it for the things to run in there, is it? Oh, there's probably still some more. So next, Giotto uses Giotto large images as the core image class, which is based on teraspat rasters. Images are not loaded into memory when the object is generated, and instead an amount of regular sampling, so like regularly spaced sampling from the image, appropriate to the zoom level requested, is performed at the time of plotting. If you're interested in how exactly that's done, I do recommend that you take a look at Giotto visuals. Resample or sample. Oh, auto image resample. So that's described in this document over here, which I'm not going to cover in depth right now. Just do note that if you want a higher resolution, you can always change this particular option over here to be a lot higher than like 5E5, maybe like 5E6 or 7. 8 is kind of heavy. Do note that as you increase this, you would expect the plotting options to take longer and longer. But that's how, this is basically how Giotto managed to plot images in a reasonable amount of time. Um, yeah, so Giotto large images are the core image class, and it basically acts as a pointer from which you can sample out image values and then put that into a smaller resampled version of that image. Spat shift and rescale operations are supported by Terra Spat Raster by default. So this is the underlying class that we have inside of Giotto large images. We inherit those functionalities for spat shift and rescale. Spin, flip, transpose, shear, and affine operations, however, will actually coerce the Giotto large image into a Giotto affine image. So this is much the same as the large image, except it does contain an affine 2D object as well. So this object will actually track the spatial manipulations that you perform on this Giotto affine image so that they can be applied through Magic Image Distort. And Magic is just an image processing package that we use to do this post-processing on the sampled image. We sample the values out, then we run this image distort using affine based on a couple of coordinates that we use as like control points. And that's how we end up with like this distorted, affine distorted image to map with the rest of our data. It also has alternative extent and crop methods so that these operations respect both the expected post-affine, so post-affine transformation space, and also the untransformed space, which is, you know, your source image itself. So this is just to show how the affine works on the image. I'm going to take the Giotto image. I'm going to apply an affine. Again, with piping, you just ignore the first argument because the first argument is this one. That's why it's basically implied, right? Affine, I can just write it out here. Affine of the G image aff, which is the affine 2D we've made, is going to coerce it, which, you know, G image started out. Why it's lagging a little bit. G image started out as a Giotto large image, but now that we've applied an affine transform on it, it is now a Giotto affine image. So I'm going to take that. I'm going to plot this. And there it is. It's been affine transformed. And the original was, as a reminder, it just looked like this. So all of that is entirely like a lazy or like a delayed kind of operation. If you really want to pull out the values as like a new set of information, it's not really an elegant way to do this at the moment, but we do also support that. So I'm going to just put this as like a permanent object first. What did I do there? Oh, that's because I made it a plot. So this is the Giotto affine image. And then after that, I can actually go to at funds. So basically at functions, realize magic. And you can see here that there's like a size parameter for how large you want to actually pull, you know, bake in this transform with. This is basically like how many values you want to sample. And then once you sample those values, the sampled image is going to be have a distort that's baked in, and then you can save that. Temp name, I think, is for setting what exact file path you want for it. This does save by default to like a temporary directory, and then this is basically like the image name that you save it with. We will definitely make this more transparent in the future for devs, but for the moment, I'm just going to do that, and then you can see that that's right here. It's now, instead of an affine image, it's a large image because you have an actual image raster object that actually exists in both on your disk as a temporary file and also in memory right now because it's a rather small image. Yeah, so it's been actually processed. Sorry. Oh, so I'm going to plot again the image now, and I'm also going to add in these polygon boundaries on top just to show that they actually do map well with the vector information. I am then going to plot the entire Giotto object. So this is me applying affine to G, which we loaded in all the way back then. G is the mini VisGen object that we loaded in at the very beginning. So I've just applied affine on the entire object. I think a lot of the individual smaller transforms don't work very well with the Giotto object. They don't all respond at the moment. But it's also probably better practice just to apply like a single affine transform on your entire Giotto object, just because that's a lot more, or it's a lot less computationally intensive to do it in a single step. That's the point of it, right? So we applied the affine transform on the whole Giotto object, and then we plot it with spat and situ plot points, and that's this over here. I set show image to true. You can see that the image is indeed hiding back there behind all of this vector information. And I'm applying the features. I as a named list from the RNA points information. I'm pulling out these particular features, and that's what you see right there. And that's what you see plotted as dots. The feeds color code is basically the coloring scale that I'm using. It's just rainbow again, 4 colors. Polygon color, I've set that cyan, and line size is 0.1. Yeah. And use overlap is false. Like I mentioned, that just allows it so that you don't only see the points that are actually overlapped, that have been previously overlapped by the polygons. You see all the points, even if they are not actually encoded into your expression matrix, encoded into like whatever is actually overlapped by your polygons information. Okay, so getting close to the end of my part. Currently, Giotto image objects are not fully compatible with the .omi TIFF files that that 10x, for example, provides. Terra, which relies on GDAL drivers for image loading, will find that the GTIFF driver does open some, but it's going to fail with some other compressions. But yeah, that's minutia. Sorry for going too much in the weeds there. But that's it for my portion. And next is going to be Jingxiang, who shows you how to take all of this like low-level stuff and apply it to a practical usage with actual aligning of multiple data sets.
So before we start, again, if you haven't downloaded this Zenodo repository, please do so, because we don't we did a lot of manipulation to the original text dataset, and you will need those intermediate files. So just a brief introduction of the example dataset we use. This is from the Xenium breast cancer pre-release pack. It's a comprehensive dataset released on 2022. It not only includes 2 Xenium samples, and also they have a VZM on adjacent slide, and also a few single cell examples. So for more information, please refer to the TAG's official website about this example. But we are using some of the manipulations on this dataset. So for the VZM sample, we have the H&E histology image, and we have the 55 micron spot level in expression with transcriptome coverage. And to overcome the low resolution issue from VZM, also have a Xenium example that has in situ transcripts that but there's only 300 or so genes that was covered. We also have the H&E histology image with the Xenium, also some IF image one IF image staining, which is a 3-channel Florence image, including DAPI, HER2, and CD20. Together with the in situ transcripts, they also have some corresponding centroid locations and also polygon information corresponding to that. So for that, we first need to know what needs to be registered and what's not. So for the VZM sample, the Space Ranger pipeline provides an automatic registration from the H&E histology image to the 55 micron level VZM spot image. Okay. And for Xenium, it's actually the in situ transcripts and corresponding cell centroid locations and also polygons are already in the same coordinate system, but you need to register the H&E histology image and the IF histology image if you have to the same coordinate system as this. So that being said, we will need to create a multimodal dataset to register all the modalities listed here to the same coordinate system. And we use the Xenium in situ transcript as a coordinate system because it has like physical distance information in this coordinate system, which one like shift by one of x and y coordinate represents exact 1 micron. Yeah, so now let's go to the R console. I've already loaded this chunk, and so first we take a quick look at how is the target coordinate system. So this is just create a data frame from this cells.csv file because it's going to be it will be loaded to a data frame and to show. So this is the target coordinate system we'll be looking at. So it starts with 0 and end somewhere around 7,000, and y is also the same, start with 0 and end around 5,000-ish. So this is a target coordinate system we will register everything to, and we'll register things one by one. So first we take a look at the VZM to register. We just follow the exact same thing, create a Giotto VZM object and use a tissue high-res image as the image to plot. Plots, I also added a few normalized Giotto and add statistics just for visualization purposes. And then once we have that, I also create a spat plot with the point size equals to 0. We can potentially also set the point alpha 0 so that we can see the image more clearly. Takes a couple seconds to run, I guess, to 0 so that. And now we can see that this is the image and this is the source coordinate system, and we want to register this to the Xenium in situ transcript part. So it starts somewhere around I guess 4,000 towards 15,000 also, and also there will be some like y-axis is ranging from minus 5,000 to minus 16,000 also. So first we know that the image is flipped. We probably need to flip it back to the same direction of the target coordinate system. It's just so what we can do is to create an affine image to spin the sample by 90 degrees and then flip it in a horizontal way. So this is what George has already showed you how to create affine 2D class. The first line is just to create a identical transform. So it's basically what if you see it here. So both A and D values to be 1 and B and C value to be 0. All also E and F should be 0 because you don't do any translation, and linear transform is just a 1 1. Yes. So we create this affine 2D object, and then we apply this directly to the Giotto VZM object. Now we can take a look at, yeah. So now we seems to have an image or like a source coordinate system in the same direction. Like we have this thing on the left, this in the top middle part, and this glands on the right part. Please note that the order of these transforms do matter. So like if you
You can you make the font a little bit bigger, Junsheng? Oh,
uh,
you didn't just do command equal sign, and that makes it a little bit bigger. Yeah,
okay,
that's fine. Yeah, that's probably already too big. Anyway, good. Thank you.
okay, yeah. So now we've already applied the transform. Please note that these orders do matter. And to be more specifically, if you want to do serial affine transforms, the affine matrix is calculated something like affine one matrix, and you apply the second one by adding that of the dot product before that. This percentage and one product sign is to represent. So this is the way you calculate serial affine transformations from different from like a serial transformation. And what you can potentially see is that we do and affine, greater affine, and do like do Spain affine ID and flip. And what you can see is that Spain affine, this needs to be applied first. This needs to be applied second. And what you can also see is that if you serially apply that with matrix, is going to be the same as this. So you should be the same. Horizontal. I probably made some mistakes when calculating the affine transform, but anyways, we can now apply the transformation to the VZM object, and this is what we can see from the transformation. So the next thing is that we need to register this object to the target coordinate system. And the way we can do that is to select landmarks. And landmarks is to be two set of points that defining the same location from two different resources. They could be very helpful to be used as anchors to create affine transforms. Like after the affine transformations, the source landmarks should be as close to the target landmarks as possible. So we provide an interactive landmark selection tool. So it's say this one. So basically, you want to ping the landmarks from the same location between these two plots. What we can do is to zoom in and yep, so we get this like top middle gland here, and we do the similar thing here. Like you can directly click on the plot and it will show that the landmark is recorded, and it will also show here its X and Y coordinates. And if you are not happy with the landmark select you click on, just do undo click. It will help you. And then you can move the ROI you're interested in, just to like move a little bit to of like where you want to select. You do the same, something like this. Yeah, you probably need to play around with this for a few times. Like you can click here, click here. You can do like just to mark more than one at once. You don't have to do that pairwise, but you just need to remember that you click this first and this next. So that we will do like this and this. And after the selection, just simply click down here, and it will return to the landmark as a list. So what you will see is like you have landmarks 1 representing the source coordinates, and this number 2 represents the target coordinates. Please note that since the landmark pinning, the accuracy of that is very important. When you select the landmarks, be sure to select landmarks not only in one part of the tissue, so like you can ping 1 here and 2, 3, and 5, 6. Just trying to make the landmarks spread around your images as much as possible. Because that will affect the transformation matrix estimation. Also, since the landmark pinning is very important, you can potentially change the options. This is what George just covered, because Giotto uses like a sample of the pixel values to plot the images. If you are not happy with the resolution you have, you can potentially increase this number. And also for Bayesian experiment, you usually will have a much larger dimensional image than the high res and low res image output from the space ranger pipeline. So for that purpose, you can potentially create a Giotto large image about using this microscope image and name it as full res, and add Giotto image to the VZM object, and then plot that with the sampling from the original microscope image. Okay, and so for the reproducibility purpose, we provided an RDS file of the landmarks I selected, because each time you redo the landmarks, there will be some minor shifting. So we just read the RDS file, and it's going to be the same as what we have. So I select 12 landmarks from both images, but usually you will need at least 3 landmarks to estimate the affine transform. But usually more is better, but just to make sure that you are pinning landmarks at an accurate position. And then we can use the calculate estimation matrix, calculate affine matrix function. Just make sure that the first is going to be the first in as computed as source, and landmarks is going to be computed as number 2 is be considered as the target. So if you do something like this, you have this landmark matrix, and if you do solve, it will matrix. It will give you the reverse affine matrix, and you can also flip the order to get flip the source to register from target to source instead. So this is the affine transformation we are going to make. The first is going to be the initial affine transformation we created over here. Just redo it to make sure. And the second is going to be the register from the landmarks. And what we can do is to overlap this spat plot and the GG plot of the points of centroids. See how we do. Okay. So it looks like we successfully register everything to the target coordinate system. And like we can see that the cells spread well with the image we have. You see this pixelated value is normal because it's doing the resample. And what we can do next is actually create a pseudo VZM data set on the Xenium data to show like how corresponding of the two modalities, VZM and Xenium. So what we would do is what we would need is actually to have a set of polygons, and for that we have a function of polystem to stem circles or different type of polygons to a certain centroid. So what we can do, but we will need to know the radius of the VZM polygon. What we know is that the VZM center to center distance is 100 micron, and the spot diameter is 100. So what we can do is to simply create a spatial network by setting the nearest neighbor equals to 1, actually. And what we can see here is that it's connecting to just the closest neighbor of the VZM spot. And what we can actually know that is that this value should be actually represent 100. So if we take this, we get a value which is very close to 100. This is probably some error when we introduced from the registration, but from the registration. And what we can next to calculate is just to calculate radius. If you know your the target coordinate system represents a certain amount of diameter, amount of microns, you can just do it here just by like setting center to center is 100. But if not, you can create a spatial network and get information from that. So now we first get the spatial locations of the VZM transformed VZM object, and we'll create a polygon from that. So what you end up getting is something like this. Yes, so you have all of your VZM pseudo VZM polygon created. And then what we can do next is to create a Xenium object with a pseudo VZM polygon. So for this example, we filtered only the MS4A1 and ERBB2 genes because they are corresponding to the immune fluorescence image as well. And then we just standard Xenium workflow or any other type of in situ hybridization based platform, we supply the Giotto points as list RNA and Giotto polygons to VZM. And then we calculate the overlap to create a count matrix. And we filter Giotto. We are setting this very conservatively because we just want to use this function to filter out the non-VZM polygon covered spots. And this getter and setter functions is just me trying to find a better color slip, find a better color scheme. And yes, this is what you will see from the expression pattern of pseudo VZM. And what you can see from the real VZM data by simply subset with extension of Giotto points, smaller probably. So also let's do this first. And now it looks better. And we can subset that just by taking a look at ERBB2 expression from the real VZM data. Okay, so now we have VZM registered, but there are two other things, which is H&E and IF. What we actually provided a convenience function to read 10x alpha image, which George already showed yesterday. We just need to provide a HE image alignment profile from whatever from the Xenium render output. What you can see is that note that it's going to be a different affine transformation because it's first applying the rotation and then scale at the 0, 0 of the top left corner of the original image and apply the translation last. So if you just read in this CSV file and apply that as affine, it's going to be different. So if you have the Xenium output, you just simply use this convenience function. That will help. And what we can get is this. But note that the image is flipped because of this transform for this specific image. What we can do next is to flip back. And this is also what George just showed, is that we re-render this into a Giotto large image, but just to make sure that we already capture all of these points from the of these pixel values from the original data. And this is raster image. And we can also use the Terra right raster function or Giotto large image function of this raster image and provide an output. Make sure you input this as a GeoTIFF file so that it will include the extent information as well. For example, here it starts around -2,000 to like somewhere above 8,000. And now we can check if this is good. Giotto Visuals provide a function called the GG annotation raster to manually overlay some of the images and some of the whatever GG plot you want to make on top of that. What you would need is to create an empty ggplot object and use this function to append a Giotto large image onto that. And we can replot the centroid to that. But you can potentially see that okay, yeah. So you can potentially see that this sparsity of the cells corresponding with the H&E image. The reason why the extent seems to be bigger than the Xenium output is because Xenium is actually only capturing part of this tissue instead of the whole, like capturing every single information from this whole tissue. So it has a smaller coverage. So with that, we can also add the register image information and compare RNA versus protein expression. We provided a 2 registered image from the IF. We can just use the same strategy here, which is we run this first. Because it's going to take some time to. So basically, we can use the same pipeline, which is use this convenience function, plot it, and see if it needs to be flipped or not, and then use this realize magic function to get all the pixelated information from that and replot and save this to your disk for future reference. So the next thing is, since we have both IF and RNA information in with single cell and higher resolution, what we can do is to load the polygon information from the cell boundaries. Simply do data table F read and set the column names of the data frame to poly ID X and Y. Create a polygon from data frame. This is the create Giotto polygon function we talked about yesterday, and add Giotto polygons of this to the Xenium object. The Giotto polygons, if you quickly check the Xenium object, it will have two polygon information, which one is cell and one is specimen. And then we can do the same thing to calculate overlap and create the matrix, but then you will need to overlap to cell instead of VCM, just like before. This is again, we are trying to get expression and find a good color scheme, and we can plot the spat feature plot to this. So using the spat feature plot, this does not contain the polygon information, but what each point would represent is the centroid of the cell locations here. Still taking some time to run. Probably because that my session crashes now. Yes, I will just restart the R session and we can go back here. So, went to here. So we can do the same thing here, and we can see is that this HER2 image will have the similar expression value compared to ERPPT, which is RNA. And we can also overlap to the VCM polygon, and it will show a similar pattern of spatial expression. So using this convenience function and also ping landmarks is good. And it's good to do some initial work, but sometimes you may ask if we can find a way to do things automatically. And what we provided here is that we can use an automated transform to register image, and we provided a wrapper function of the scale invariant feature transform. So this also in short SIFT. So SIFT will first identify the extreme points in different scale space, and from this paired image, and use a brute force way to match the points. So matched points can then be used to estimate the transform and warp the image. And however, the major drawback is that once the dimension has become bigger, the computing time will increase exponentially. So if you have a lot of small images and you want to register them, you can potentially use this and to register things. So we first create the Giotto large image of these two mini images.
Yunshan, you still have around 30 minutes. So if you need to rerun parts of the code, don't worry, you still have time.
Okay, yeah. Yeah, we actually don't have to rerun this because it's a separate part. So if we plot the image first, you have some the mini HE image, it will have something like this. And if you plot the IF image, you have something like this. We are going to register IF to H&E. Just personally, what we find the most efficient way is to set the negative y equals to false, so that they are calculating in the same dimension as positive value. And also, if you need to do some flip or rotation or transpose, it's better to do it before you get into the automated registration. So what we can use this estimate automated image registration with SIFT function, and X represents the source image you are going to register. The SIFT algorithm requires the image to be processed into a grayscale matrix. So we provided a convenience function to pre-process the image to matrix. You need to input the path to your image directory and see if you need to flip the image. And if you so here we use the single channel because DAPI image usually represents the tissue structure better than overlap of like 3 different fluorophore. So sets the use single channel equals to true, and single channel number is 3 because it's the DAPI. And Y represents the target image you need to have it to. This invert function is that I found usually be pretty helpful because the H&E, if you convert that to the grayscale, so going to make the plot match equals to false. Probably removes the Giotto environment myself, but yeah, you would need the scikit image as part of the scikit image platform. And we note that there's an update of scikit image, and which will probably mess around with the plot match function. So if you also have that issue, you can just put this plot match parameter into false, and the max ratio is the parameter you use to match the descriptors. Yeah, I'm probably just not going to run this now. And so if we successfully run this command and you turn on the plot match, it will result in a few descriptor match from the source and target image. And use that, we can so the output of this function will be a list of the output from the estimation wrapped from the scikit image. And you can simply convert that params into a matrix and apply the affine image to with this matrix. And you can see the overlay of the registration result. There's some final notes is that the image registration is becoming crucial for spatial multimodal analysis. The methods shown here are all linear transformation ways to register images, and they are good to for some initial registration purpose, but for more accurate, like subcellular level resolution study, it's going more advanced registration strategies will be needed. Right now, a lot of groups are providing like different tools that can be, some of them can Giotto already support them. So, like if you have images registered to the target coordinate system, you can load it directly to Giotto. Yeah, but we'll keep working on it and try to update in the future.